So the paper that I'm going to present is Understand the Early Iron Age Technology from Rithi Ranjana. And I have not given an introductory slide for Rithi Ranjana because I supposed that Dr. Nikhil Das would present on earlier before me on Rithi Ranjana because he's the actual excavator. And I'm thankful to Nikhil Das for allowing me to work with his material and taking it up for my postdoctoral analysis. And I would always like to thank a few people because without the Archaeological Sciences Center and the National Metallurgical Laboratory of Jamshedpur, I could not have gone ahead with my analysis. So the aim of the work is basically to reconstruct the missing links between the beginnings of iron technology and of the megalithic early Iron Age period of Vidarbha and the early historic phase. Because when we, if the earlier works, if you check the earlier works, the excavation reports only talk about the typology. They say this is axe, this is knife, this is dagger, and it goes on. And again, with the historical phase, when it comes to iron, it is being ignored, or again, it is being done only based on the classification, based on typology. But that is not where we should end. Because when we are talking about technology, we should talk about the making of an artifact, the uses of those artifacts, and how was it formed. And to understand all of these, we need to know the functionality and also the provenances of the iron ore that was being used. And this work will also aid in reconstructing the ancient Indian iron technology of the period, which is void of any literary record. Because I feel the Sangam literature talks about a bit of the southern Indian megalithic period, but for Vidarbha, we have no written records. So this is absolutely based on field reports. And by piecing the puzzle, the ferrotechnological continuation between the early Iron Age period and the early historic period really needs to be linked. Otherwise, technology, which forms the society, and when we are saying early Iron Age society, that means we are focusing on the technology, but unfortunately, not much work has been done on that. So this is basically the map of the study area, as you can see, which is Vidarbha, which is part of Maharashtra. And I am concentrating my work in Nagpur, Gondia, Chandrapur, and Gadchiroli district. I'll tell you why I have concentrated on these regions. Why Vidarbha and why Nagpur district? Why, when I talk about early Iron Age Vidarbha, why am I concentrating on Nagpur district? Because one major important thing is that the entire mineral deposit of Maharashtra is concentrated in Vidarbha. And the 90% concentration is in Chandrapur, Gadchiroli district. And all the megalithic sites or the early Iron Age sites of Vidarbha are located in this region. So we can link. So when I talk about this, the work of B. Subbarao comes to my mind. That every area the area actually says what sort of technology will develop there, and it is based on the natural resources. Because if you have abundant natural resource, then only your technology can develop, because you need to practice with it. You need to have failed attempts, and if that natural resource is not available to you, you cannot practice with it. So as you can see, the Dharwar period is basically when all these mineral deposits are formed, where we have copper, chromite, gold, graphite, iron ore, magnesite, manganese ore, mica, and talc. And for us, iron ore is the most important thing here. Second thing, why again Vidarbha? It is coal. Coal is present only in Vidarbha in the whole of Maharashtra, and it was formed when the Barakkar formation of Damodar group, and the deposits are found in Nagpur, Chandrapur, and Yotmal district. So you see, Nagpur is the common place for both iron ore and coal. And coal is required to run a furnace. So when I'm talking about early Iron Age, the first thing that comes to your mind is the iron ore deposits. Because if your iron ore deposits are not economical, then a technology cannot develop. And it is very important for us to study the iron ore deposits to understand the provenancing of the iron objects. So the iron ore is naturally found only in Chandrapur, Gadchiroli, Bhandara, and Sindhudurg district. And Bhandara is the only place where we are getting the magnetite form, the titaniferous magnetite form. So when we are getting titanium in our iron ore, in our iron of an object, I can blindly say it is that iron has been quarried from Bhandara. And the richest and the most economic deposit is at Lohara, which is located in the Chandrapur district. And the latest record, which is on the dossier of the iron ore deposits, 2006, it says the iron ore deposit of Lohara has 81.22% of Fe2O3. And but Lohara is not. The iron ore from Lohara is no more in use now because it is basically the heartland of the Naxalite region. And the hematite type of iron ore is not a common occurrence and is found from Gondia district, from the mines of Khursipur and Ambetalau. And the titaniferous magnetite ore with the vanadium inclusion forms part of the Amgau group. So when we get vanadium in an iron object, we know it comes from the Amgau group. Yeah. When it from the titanium, we know it comes from the magnetite group. And then when we are getting, and there is a record of high hematite, we can say it comes from the high hematite sources. So as you can see, this is one of the earliest record of the indigenous iron smelting, and it goes back as early as 1873. And we have the reference of a group called Maharatas in Chanda Central, which is basically the Chandrapur district. And this group, they used to actually utilize the anhydrous hematite of this Lohara area, Lohara iron ore region. And as you can see the entire chemical composition, and this forms our major primary record to match our iron ore objects with the chemical composition of that region, because getting the record of Lohara is very difficult now because it is not in use. So why would our government or the iron ore ministry spend money on analyzing? Even if they analyze only the iron percentage and the silica percentage. They do not go down to the 0.00% of any element. And for us to understand the provenance, we need to go down to the 0.0000% of any element. So now let us come to the sites that I am dealing with. As you can see, the site Rithi Ranjana, which is just below Nagarthan and just beside on the left hand side of Adam. And you can see I have plotted these sites in association with Naikund. And everybody knows that Naikund is very important for our study, because Naikund is the area from where we get the first evidence of furnace. And the earliest metallurgical work was done at the site of Naikund by Dr. V.D. Gokte. Because from there, I have actually continued my work. If that work wouldn't have been done on Naikund, I would not have ever got the idea of working on the samples from there. And I actually dedicate all my archaeometallurgical work to V.D. Gokte. So you can see the sites that I am concentrating at the present moment is Naikund, Rithi Ranjana, Nagarthan, Ubali. Why I'm concentrating on these sites, I'll clearly say, because I'm looking at the transition from early Iron Age to early historic. Here, Ubali is a megalithic site, megalithic early Iron Age site. Naikund is an early Iron Age megalithic site. Rithi Ranjana is an early Iron Age habitation site, which on evidence of habitation of the early Iron Age period is very rare. We have got from Takalghat Khapa and we have got from Bihar. So when we're getting evidence from habitation, it is very important to analyze that. And Nagarthan also gives us a habitational layer, but no megalithic. So I need to compare between my iron objects of the megalithic period, early Iron Age megalithic, and the early Iron Age habitation, and the early historic period. And Nagarthan gives me a multicultural deposit from the early Iron Age habitation to the early historic habitation. So that is basically, Nagarthan will give me a series of data to compare and contrast with it. So now, as you can see, I the concentration of this work is on the site of Rithi Ranjana, which was excavated, I think, in 2017. And it actually was noticed and became important because it is one of the very few sites, as I've earlier said, because it's a habitation area. Getting a habitation deposit from the early Iron Age period is very rare. And everybody actually wants it, but people hardly get it. Getting a megalithic stone circle or a cairn circle in Vidarbha is common, but getting a habitation deposit is very rare. So basically, as you can see, what I have done, my methodology is to classify all the iron artifacts first, morphometrically, typologically, based on the functionality, not just on how they look, but shape, size, doing a statistical study, because there the length, breadth, thickness also matters, because then you can understand the standardization that was being practiced by them. And finally, taking a bulk of sample down to a handful of sample, because you cannot sample every other artifact that you're getting, because after all, these are antiquities. These are not just something lying on the road, and antiquarian law doesn't allow that. So getting a few samples to do your later scientific analysis, which would help us to develop the technology. So the major categories that have been understood from the iron artifacts are: these were tools for architectural activity, that is basically carpentry or woodwork, tools for agriculture, tools for defensive and offensive purpose. So these are the three major categories that I have segregated my artifacts into. Why Rithi Ranjana? Again, Rithi Ranjana is very fertile and rich in mineral deposits such as manganese and iron ore, and this site is actually located on MOIL, Manganese Ore India Limited. Because that is basically a government company which queries manganese ore. So the thing actually reflects in our face that this an iron and megalithic site is actually standing on the deposit. And this site actually developed because of its easy availability of iron ore, which is conducive for settlements to develop during the early Iron Age, as we see in Nagpur or Chandrapur and Gadchiroli region. And the artifacts that were studied, there were about 68 artifacts comprising of household, agriculture, then offensive, defensive purpose, woodwork, and the methodology, as I said, was first to categorize them according to the functionality, doing a statistical analysis, and then going ahead to do the scientific study. Because before doing the typological analysis, if we go for the scientific study, again, it would be half the job done. So 19 samples were selected from these 68 samples to be studied under microscopic and chemical analysis. And the problem is that once I've selected 19 samples and I've got it back to the lab, when I started preparing the samples, only 12 samples were found suitable. Because to do any microscopic study, we need a metallic core which is existent. But half of the samples, it looks intact from outside, but then actually the encrustation and the corrosion has infiltrated so far that it is just rust, which just collapses or just crumbles in your hand once you cut. Or it is so rusted that it is absolutely porous and we do not have any metallic core left. So the next slide shows how do we prepare the samples for metallographic study. Here I have given you something like a knife, and you can see the shaded regions are basically the region which is intact, and the dotted regions are the rusted regions. So you have to actually understand from where you need to take your sample, because you want your non-rusted region. Because if you get a rusted region, first of all, it's very difficult to prepare your sample, and then you might not get any image out of it. So a non-rusted region or partly rusted region was cut out from the sample, and then it was mounted using PVC resin, and we have a epoxy powder, and you actually mount that sample in the PVC pipe. And here you can see this is the mounted sample. So after mounting the sample, we have to go through stages of preparing the sample. You have to do stages of polishing on the roller, then on the emery papers, which you have stages, and then you finally you have to basically do a chemical treatment on that, because you have to actually focus on the non-rusted area. So we have to treat it with ethanol, and then it is ready for scientific analysis. So when I'm saying ready for scientific analysis means it is ready for optical microscopy, and same, because chemical composition is a chemical analysis is a very different procedure again altogether. So what you can see here is a knife fragment, and the hardness, because here the carbon content and the hardness is also very important, because when I'm looking at the carbon content, it is a high carbon steel, because the carbon content goes up above 1, and the hardness is 532.8, and the hardness here is very important because high carbon means the hardness of your artifact increases, and that actually helps me to prove the functionality of my artifact. Because an object which should be used for cutting or chopping or maybe even butchering, it needs to be hard. It cannot be done with a soft metal. So as you can see here, we have the eutectic phase, which is the alpha plus beta. Alpha is basically the prime ferrite, which is in association with the eutectic phase. Based on this granular structure and the carbon composition of the material, it is determined that it is of high carbon steel. You can see here that you have a very prominent grain phases. Here the border lines are very clear. The black border lines are basically the carbon which is settled along the grains boundaries, and you have a proper perlitic formation. This microstructure is basically a perlitic formation. Then you have a ring fastener. As you can understand, ring fastener is not something which will take the pressure of your activity. Ring fastener is actually used for hafting an object. So it will just hold your object with your wooden structure. So it need not be very hard. And that is again proved by your carbon content, which is 0.61, which is basically low carbon steel. And the structure also proves that the cellular structure is not perlitic, it is more towards a ferritic structure. And during the solidification was basically a slow cooling method. And from here we can understand they knew how to heat it to a temperature, red hot temperature, and then they needed to cool it down by placing it onto the ground and let it cool down according to its natural condition, and not plunge it into hot water or hot oil, so that the surface gets hardened very fast. This surface did not get hardened very fast, so it is not very brittle. It hardened according to the carbon that was absorbed by the cellular structure. And the cellular structures show it is a low carbon steel, and the lamellar formation is distinctly visible under the scanning electron microscopy. Then the next artifact that has been chosen is of a nail. Why do we use a nail? We use a nail to fix something for basically carpentry work. So the carbon needs to be high enough for it to not break, but it need not be as high as a knife or a dagger, because nail will not take the pressure, because there are multiple nails in your table. So it is not just one nail which is taking the pressure of your artifact. So here you can see the carbon content goes up to about 0.7680%. And the iron content is 78.87, which is very high, which also why this elemental study is also important for us, because here we can understand that the smelting procedure was also pretty advanced, because otherwise maximizing your iron content over your silica content, which is maximum in your ore, is very difficult. If you cannot achieve your smelting procedure properly, if you do not know how to control your temperature, if you do not know how to control your carbon, then your smelting procedure will not be economical. So here you can see your hardness is 5.503, which is hard enough for a structure to hold. Then I have taken the sample of a knife, and here also you can see it's a very clear perlitic structure where perlitic means, let me clear, it is basically a steel formation. Within steel also we get high carbon steel, low carbon steel, and this is basically a high carbon steel structure because you have very clear granular formation. And here you can see these are basically the grains, and here you can the carbon compounds, and this is basically the rust formation. This black is the rust formation, and the carbon content again is high carbon steel 1.0560. Now getting a carbon testing done is very difficult because here I am not depending on XRF or XRD for my carbon content. I am doing only carbon content, which is available in only one place now in India, which is the National Metallurgical Laboratory in Jamshedpur, because nobody uses it now. And that is you are using for the carbon analysis will be of no use because it is combustible. The entire sample is wasted. Here you can see the EDAX that has been done on the sample. We do multiple spectrums, and to do the EDAX analysis, we need to do it in a vacuum instrument, and that is basically done by using liquid nitrogen. And again, doing EDAX is basically you are again destroying your sample, because to get analysis out of your iron artifacts, you need to do gold coating, which cannot be removed later. So if you do a gold coating on your sample to make it conductive, then your sample will be of no use later. So again, you can see why I have used this spectrum is, and I have read those elements that is of importance, that is the cobalt, vanadium, nickel, sodium, chromium, then we have manganese, we have potassium, and we have sulfur. These elements are important for us to do the provenance analysis, not iron, not silica, not aluminium, because those are present in all your iron deposits. But cobalt, vanadium, nickel is not present in all your deposits. Here you can see titanium is not present. So we can rule out the titaniferous magnetite. So we have to concentrate on those where we get vanadium, cobalt, and nickel. And we have to zero down by looking at the spectrum, by looking at the composition, because this composition or the atomic weight or the percentage of the element in that iron deposit should match with what I'm getting from my sample. Plus minus 5%, because that when you are doing a smelting procedure, some percentage actually disappears, but then it should be near to what is there in your records. The next sample that is very important for me was it was basically an ingot. And why I'm saying it's important, because this proved that the later stage of melting was done at this site itself. I'm saying melting and not smelting, because for smelting you need a proper furnace. You need to take the temperature above 1130 degrees Celsius, where we do not have a burning patch. You do not have crucibles. You do not have cinders. You do not have tueres from the site of Rithi Ranjana. So it must have been, the smelting must have done at a place somewhere else. And the melted iron in the form of ingot was got back to the site. And again, the procedure of heating up and then manufacturing an artifact from the original ingot was done. So that is very important for us, because we have got the ingot sample from this site. And as you can see, it is basically cast iron, where the carbon content is very high. And here you can see the carbide flakes. The black things are the carbide flakes, and no forging has been done, because you do not see any the cellular. There is no the cellular structure has not been flattened. Because if there is any quenching or tempering or even forging marks, then the cellular structure will be flattened along the axis. There is no flattening of the cellular structure, and it has been the thing has been melted and cooled into a desired shape, because the thing of quenching is visible based on your grain structure. Then we have stylus. Here, the stylus, as you can see, it's intact. But when I cut it and went inside, the sample was extremely corroded, and I could not get a very good microscopy done. But the granular structure was visible, and we could understand it's a pearlitic formation. But doing a TEM on this would have been better off, because you have a TEM actually requires very small area and gives you a very high magnified image, but that is not available to us at the present moment here. Then the next important thing was an arrowhead. This arrowhead actually brought in a lot of question in my mind, because the carbon, which is 0.4662, is very low. Because as you can see, arrowhead, it is used for, it's a projectile tool. It will be thrown from a distance, and then it will get stuck to something. So once it gets stuck, if it hits, then it will break. If it doesn't go through, if it goes through, that's a different thing. If it actually boomerangs, then it will hit it, then it will try to come back, and when it hits it, it will break, because 0.46% is a pretty low carbon, and it will not make the structure very hard. So, and but I wanted to look at the microstructure, and that again created an issue, because it was extremely rusted with very negligible core area visible. And the only thing I could understand, the black sections were the blackish sections were the oxidization and the rusted surfaces. So this actually made me understand that all that glitters is not gold. This object looked to me very nice, but actually I couldn't get anything out of it. The next artifact that was chosen by me is basically, you can see that there, if you look at the report of many other sites, you have beautiful horse ornaments, you have beautiful axes, you have beautiful daggers, you have wonderful awls. But then for an archaeometallurgist, samples available are these, because these can be used or can be discarded by the excavator, because they're not that much important. But horse ornaments like stirrups and awls and borers, they're important for the excavator. So we never get those for sampling. So again, there is a problem, because I cannot sample a major part of the assemblage. So again, you can see here we can see forging has been done. So basically the artifact was cooled. It came down to the room temperature, not from the red hot temperature. It was heated again. It was in the solid form, and then it was forged. That is why you get those black lines along the surface. It shows that the grains were flattened, and the recrystallization of grains have taken place due to forging and the temperature. And this structure actually helped us to understand the melting temperature. And this structure generally goes towards 0.3 melting temperature. And it is understood from this that the smaller grains have better durability and very good strength, because the grains are nearer to each other. We do not have very broad boundaries. So what do we understand from this? We understand a few things. First of all, that there was a marked rise in the carpentry artifacts such as nails, clamps, and rivets. And secondly, we understood what were the procedure that was used by the early Iron Age ironsmithers at the site of Rithi Ranjana. Till date, we know that these artifacts are nails, maybe engraver, maybe axe, maybe borer, maybe awl, but nobody actually tried to understand who made it and how did they make it. Because if we do not understand who made it and how did they make it, we'll never be able to understand the technical failures that they had to go through, or the technical disabilities that they had, and what did they overcome. Because making steel at that time without having a thermocouple, without knowing how much carbon your iron is actually imbibing, it is very difficult. And they actually knew how much carbon the surface should imbibe and how much carbon is needed to make a high carbon steel. And if they did not know, their artifacts actually failed. So we actually get failed attempts, we get steel, we get cast iron, and we get wrought iron. So we get stages in the production of iron. It's not that we only get the developed or the advanced form. We also get the process through which they are doing it. So it actually helps us in developing the cognitive ability to understand the mindset of the Iron Age smithers. The inferences. The inferences that I have been able to draw from this is basically the scientific analysis on various artifacts from the referred megalithic sites, that is Rithi Ranjana, Nekun, Bihar, Mahujari, Khairwara, Bhagibhori, and Borgao. Rithi Ranjana is part of my postdoctoral work, but Naikun, Bihar, Mahujari, Khairwara, and Bhagibhori, and Borgao was part of my PhD work. So that data is there with me. So I could match that data, my megalithic site data, with my early Iron Age habitation data, and based on the chemical analysis, chemical data, compositional data, and also the technical data, we understand that the common source of ore, that they use the common source of ore because the chemical composition remains the same. And if not the smithery, because smithery also we do not get any evidence from Rithi Ranjana. We get evidence only from Naikun, which is at just a small distance from Rithi Ranjana. And from Rithi Ranjana, we get the evidence of smithery. So if we match the artifacts from Naikun and Rithi Ranjana, we can develop the trade nexus that followed. And to understand that there was a common source of smithery also, we have to again go back to our GSI record, where we have the record of Maharattas that I have referred earlier, that these Maharattas used to be the smelters. They were never the smithers. They were the smelters. And the bloom for the raw iron that was used, that was made into an iron ore, was actually bartered by them with the smithers, with the lohars, and for some money, for some grains or for some animals. Then these lohars used to take these smelted iron and then rework them, and then they used to make iron, they used to make artifacts out of it. So maybe Naikund was just the place where smithery was done and smelting was done somewhere else. So the original artifacts that we are getting, we have to trace it back not only to Naikund, which is a smithery place, we have to trace it back to the group of smelters who was somebody else. So we can see that entire process that is being happening at this area of early Iron Age Vidarbha. And secondly was the smithy techniques adopted by the smithers at the habitational site of Rithi Ranjana reflects a similarity. When I'm talking about similarity, I'm meaning standardization with the iron artifacts recovered and analyzed from the above referred megalithic sites, thus establishing the cultural relation between the habitation and megalithic sites. I did not go into the data from Nekun, Bihar, Maus, because that would have been very less. That would actually go up to about 1 hour. And because I have studied almost 1,000 artifacts. So I can say that what you are seeing in Rithi Ranjana is actually reflected at all the Iron Age megalithic sites. So there is a similarity in the length, breadth, thickness, or I won't say the exact length, breadth, thickness, but the ratio. Which is actually calculated by using the R software, where if the length decreases, the breadth will decrease and the thickness will decrease. But the ratio between the length, breadth, and thickness will remain the same. So that has been actually, that is reflects in the assemblage from all these sites, thus establishing the cultural relation between the habitation and the megalithic, which is very important for us, because we were getting only megalithic data and we were not getting any habitational data. This actually puts an end to the age-old controversy of who were the builders of the Vidarbha megaliths. Because as people, there were always a question, we are getting only megaliths, we are not getting habitation. So why aren't we getting any habitation? Were the people who were building such beautiful megaliths, were they not staying? Because they have been always saying they were nomadic cultures. Yes, and again the question arises, if they were nomadic community, then how did they have the time to produce a varied range of artifacts? That means they were engaging in agricultural activity. They were engaging in carpentry. They were engaging in animal rearing. Otherwise, would there be a need to produce such artifacts in their habitational records? No. So that, I think for me, that puts an end to that controversy. And the types of artifacts that is projected is a wide range of variety, and surprisingly diminutive miniature artifacts are absent, which is present in the megalithic culture, megalithic zones. So basically we can very comfortably say now that the diminutive axes, the diminutive rapis on the edges that have been, or the nail parents that have been found from Bihar, Mahursari, Khairwara, Bhagimori, with embedded in the stone circles or the interred with the dead, they were specifically made for interring and not for usage and the habitational deposits. My presentation ends here. If anybody has a question, I'm open to it.
Thank you, Oishi.
Sorry, I missed out because my PPT wasn't moving. I had just another slide to go with it. So the main thing is that most of the iron artifacts that have been contextually recorded from the archaeological excavations in India have been always typological in nature. So the ancient manufacturing knowledge system and functional utility of these artifacts were hypothesized with the help of references in ancient texts and colonial records, referring to traditional iron smithy communities, which is very important for us. We have the GSI record where they're talking about the Maharathas. So we know there was a trade nexus at that time. It is a barter system. So why can't, when we look at Vidarbha or the Iron Age data, we need to understand that maybe the trade nexus is not visible in our archaeological record, but it was there altogether. Everything was not being produced at the site. That is why we do not get the remains of furnaces at Bihar, because it was being brought from somewhere else. And this work is for the first time that the reconstruction of the ancient Indian knowledge system on probable steel manufacturing is attempted through the metallurgical and composition analysis of varied early Iron Age artifacts found from Vidarbha on a major scale, and it encompasses nearly all the excavated iron assemblages from the early Iron Age sites. And I'm still trying to get more samples. I'm working on another site known as Ubali, and I hope it can form a strong database which will be used by later researchers who will work on the megalithic sites. And I really want people to work, because otherwise these iron artifacts are just getting rusted and corroded sitting in your cellars. And final slide, I would really be thankful to the organizers, Abhayan and Rajesh Bhaiya, for actually asking me to present, because I really want to speak about Vidarbha. And to Indian Institute of Technology, Gandhinagar, because that is from where I was doing my postdoctoral study with Professor S.P. Mehrotra, Dr. Amit Arora of Metallurgy Department, Michelle Daneno, and Dr. Alok Kumar Kanungo for actually allowing me to work on the topic that I wanted to work. National Metallurgical Laboratory, Jamshedpur, for allowing me to do my analysis there, and Rockwell hardness test and my carbon analysis. And of course, my guru, my guide, Professor K. Krishnan of Department of Archaeology and Ancient History, MS University of Baroda, without whom I would have never known that doing archaeometallurgical analysis would be so much fun and easy. Thank you.